Okay, guys, so welcome to another DSA copy. Today I will talk about algorithm analysis. Alright, so in algorithm analysis, I will talk about in this copy. So I will do this in two parts, part one and part two. In this one, I will do big O notation, big omega notation, and big theta notation. Alright, and in the second one, I will do frequency counting method and algorithm analysis. Alright, so let's get started. So let's start by asking the question, what are these notations? So we had big O notation, big omega notation, big theta notation. What are these? Okay, so what are these? They are known as asymptotic notations. So an whatever this word is, a notation is a notation that is used to analyze uh, a function as it reaches infinity. So these notations are used to see to understand a function's behavior as the function goes to infinity. So that's what these functions do. They give us a rough estimation of a function's behavior. So that's something what we have to keep in mind, that these three notations are used to analyze functions. They aren't necessarily used to analyze algorithms. They are used to analyze functions, and mainly when a function is reaching towards infinity. So because of that, I have a small request from you guys. For this copy only, completely forget about algorithms and focus on functions. Today, in this first part, we will try to understand how to analyze functions using those three notations. All right. So forget about algorithms for now. So let's start. So what is big O notation? So big O notation gives us the upper boundary of a function. So if you guys have seen functions before, graphs, they variate between values. They go up and down. And big O notation gives us an upper boundary for those functions. So if we take a look at the formal definition, so this formal definition is a little bit hard to understand, but let's go through it quickly. Fn is O of Gn if there exists positive number C and N naught such that Fn is less than or equal to C times Gn for all n greater than or equal N naught. Okay, so that's the formal definition. Let's put that aside and break it down one by one. So what does it say? It says there should be two functions, Fn and Gn, and Gn should be once you multiply Gn by a constant, it should be greater than Fn after a particular N naught value. So that's what it says. So C has to be a positive value, and n naught can be any value. N naught can be either positive or negative, but in algorithm analysis, n represents the number of inputs of to a particular algorithm. So number of inputs can't be a negative value. Therefore, in algorithm analysis, we say n naught is also positive. But if you are taking look, if you are looking at this from a mathematical perspective, n naught can be either positive or negative, absolutely no problem. But in algorithm analysis, because n is positive, n naught has to be positive as well. Let's quickly do a small example so you guys have an idea what this big O notation is. So let's say there's the function fn such that fn equals 5n plus 8. And then we have a candidate for gn. Okay, at the moment we don't know whether the gn we have over here. Okay, I have said gn equals n. It's just a candidate. We don't know whether that's the actual candidate or we might have to change it later. Actual value, or whether we would have to change it later. For now, it's a candidate. So what we do is that we multiply that candidate by a constant and see whether it satisfies the definition. So over here, If we apply 15 as the constant value, we can say that 15 times n will be greater than 5n plus 8. If you apply 1 to n, so if when n equals 1, 5 n is 5 and then 5 plus 8 is 13, where 15 times n is 15. And you can keep adding values and it will evaluate to true. Later, I will show you guys how to do this using limits. All right. Uh, but for now, let's just go with this simple way. If you guys aren't familiar with limits, there's a copy done by Rivin, which he did a long time ago. It wasn't a really long one, so better check it out and come back to this one. You will need limits to find out whether GN is the correct candidate or not. All right. So yeah, this is how you find out whether a function, whether what is big O of a function. So over here we have small graph. Hopefully this will clear things out. So we have this fn. Okay, this is the function. And then we have gn. Once you multiply gn by a constant c, it has to be greater than fn after a value n naught. So if this condition is satisfied, that means gn, so c times gn acts as the upper boundary. We say this function belongs to the gn class. So in another way, we can say finding the big O notation can be defined as finding to which class a particular function belongs to. Okay, if you guys find this a little bit confusing at the moment, just hold on. It will all clear up as we go through the slides and once we do some questions. All right, just hold on. So over here, so if we go back to the previous example, over here we say fn, fn, which is 5n plus 8, belongs to this on class. All right. So when we say that, we ignore the constant value and we get only the value with the function gn. So wait a moment. So some of you okay, that looks better. Okay, so let's say there is another function. Okay, why isn't this writing? There we go. Okay, so let's say there is another function such that fn equals 3n plus 7 or something. So even for this function, big O will be n. So for both of these functions, big O was the same value. So both of these functions belongs to the same class. All right. So that's another way of looking at big O notation. So if we go to the graph over here, it says that gn can be any function. It just has to, once it's multiplied by a constant, it has to be above fn. Don't think too much about this. This is a very simple concept. It just gives an upper boundary. Okay, so an upper boundary is a function that stays above fn after a particular value. So someone might can argue we can take n square as gn as well. Well, that's actually true as well. So not only you can get n and any other function that's greater than n as values for gn. So here we say what we take n squared as gn, and then we compare it with the definition. Over here we have uh, the inequality that it needs to satisfy, and obviously n squared is going to be greater than fn plus 8 after a particular n naught value. You can find that after doing some calculations. All right, because of that I can say fn is O of n squared as well. So it's kind of like this. So let's imagine you are in your room and you're jumping up and down. Obviously you are jumping up and down between roof and the floor. So you, no matter how hard you try, no matter how how hard you jump, you will always be below the roof. That means you will always be below any other margin that's higher than the roof as well. So you can say you can jump up and down between the floor and any other margin that's higher than the roof. If you are always between roof and the floor when you're jumping up and down, you can say you're going to be in between any margin that's higher than the roof and the floor. So technically, you can say that you're jumping up and down between the sky as well, sky and the floor. That's also correct. Well, it is correct. You can use any margin that's higher than the roof to give yourself an upper boundary. So in all these three scenarios, in this scenario, roof is the upper boundary. In this scenario, this something higher boundary acts as the upper boundary. It also acts as an upper boundary. And then in the third one, sky can be your upper boundary as well. So it's about finding a boundary that's higher than the function. So it's about finding the upper boundary. All right. So if I say a function fn is a big O of a particular function, it is also, so any other function that's higher than that function acts as the upper boundary. So in this situation, in our previous example, we said fn is O of n, which means n acts as the upper boundary of fn. That means these functions which are greater than n also acts as the upper boundary of fn. So technically all these are correct as well. So we have fn, we have O of n, which is the tightest boundary. Okay, it's like the roof. It's the tightest boundary. And then we have these other functions that's greater than n, which also acts as upper boundary. But they are not far away from the functions from how fn varies. So technically, we can use any of these functions as the upper boundary. So keep in mind, big O is about finding the upper boundary of a function. That's all that it does. So it gives us a rough estimation that no matter what value the function gets, it won't go above this upper boundary. So it just gives us a boundary where the function behaves. But we need to have an idea about the behavior of this function. So for that, to get a proper idea, to have a good estimation, you should use the tightest boundary possible. So let's say that you go up to a person and say you can jump up and you can jump between sky and floor. You go up to a person and say, I can jump very high. I jump between sky and floor. Well, it's correct. Sky is the upper boundary. So you are obviously jumping below the your upper boundary, but it doesn't give a very good idea to whoever the person that's listening about your jumping abilities. If someone comes to you and say, if you go to some person and say that you can jump between roof and floor, it gives a better idea because the boundary is tighter. So it gives you a better idea. Therefore, when you are getting the upper boundary, you should always go for the tightest boundary. Other boundaries are also correct. Okay, n squared, n times log n, 2 to the power of n. They all act as an upper boundary for this fn, for this example. But we need the tightest boundary. So therefore, we go for big O of n. We go for n, not square, not we don't go for n squared or any other one. All right. So that's all what big O notation is. So we have this scary looking definition. Okay. So we have this scary looking definition. What it says is basically given in this graph over here. So what it says is that there should be a function gn. Once that function gn is multiplied by c, it should be above fa after value n naught. That's what this definition says. Fn is of gn. We can say Fn is of gn if and only if gn satisfies this condition. So there's this condition. C times gn has to be greater than Fn. So let's say for an example, you have a function. So let's take a quick example. Okay. So let's say we have Fn equals 2n squared plus 5n. Okay, so if I draw the graph, okay, it's not very accurate. So it's gonna look something like this. All right, and then you're gonna have what? Well, let's say you take gn equals n as the candidate. So it's gonna go like this. Okay, now let's go a little bit above. So it's gonna go like not the best day to draw that. Something like this, yeah. So let's say. So in this scenario, gn is not, no matter no matter what value you multiply gn by. Okay, let's say that you multiply gn by million or something. Then gn times million will go like this. So let's say gn times 1 million. Still, after a particular n naught value, as these both functions goes to infinity, after a particular point, fn will be greater than gn. So no matter what value you multiply it, you can't use n as the you can't say fn is, for this particular example, fn is okay. So yes, that. For this particular example, you can't say fn is O of n because this doesn't satisfy the condition. You guys will have a better idea how to find gn once I go through the how to use limits to find this. Until then, just hold on. All right. So yeah, that's big O notation. Big O notation is about finding the upper boundary. Once you find an upper boundary, any other function that's greater than the value you found can be used as the upper boundary as well. It's also correct. If fn is 5n plus 8, we can say any of these values starting from O of n act as the upper boundary of the function fn. All right. So then there are some characteristics of big O notation you should be familiar with. So if a function fn is O of gn and gn is O of hn, we can say fn is O of hn. Fn is O of hn. Yeah. So let's go to the whiteboard again. So what I'm saying is, so let's say we have a function fn equals 5n plus 8. We can say, so in this particular scenario, the tightest boundary is O of n. we can say Fn is O of n squared as well, because n squared is greater than n, it's also valid. So in this scenario, Gn is n squared. We can say Gn is O of n4. You can use n cube as well. It's also correct. So this one is correct. So in the same way, we can say Fn is O of n4. So that's what I'm saying over here. When I say so, this was in Manjush's note. When big goes transitive, that means if Fn is O of a particular function, and that if particular function is O of another function, we can say Fn is O of that third function. So the second one is, if there are two functions Fn and Gn, where both belong to the same class, the addition of those two functions belong to the same class as well. So let's say we have an Fn where Fn so Fn equals 5n plus 69. Okay, so we can say it belongs to this. But when we are analyzing the function, we use the tightest boundary, but we can use any other boundary as well. Any other boundary that's higher than that. But when you're analyzing, we use the tightest boundary to get a proper estimation. All right. So that's when it comes to analysis part. Right now, we are just applying these two functions. So we have Gn. Gn is 3n squared plus 8n, which also belongs to the class n squared. So if you add those two functions, you get 3n squared plus 5n plus 77. And that also belongs to the same class, n squared. Okay, you can do some calculation and find out whether it's correct or not. So yeah, for now, let's just use this rough method. And once I go to limits, you guys have a better idea how this works. All right. So yeah. So and then there's this last one. What it says is that the function log a to the base n is log n to base b. So let's see what that means. So let's say, okay, there is a function. There is a function fn that is equal to log a to base n. Okay, that's n. That should be okay. So in the last semester in our maths module, there was a theorem that it said you can write a logarithm like this. B to A. Okay, you can rewrite this logarithm in this way. So over here, both A and B are constants. Okay, because of that, log B to A is also constant. Therefore, we can say log A n is equal to 1 over log B to A times log B to n. Over here, this is a constant. Okay. So we can say log A to n equals C times log B to n. In this scenario, we can use this as Gn. This one is our Fn. And if you recall the definition, it said Fn has to be less than or equal to C times Gn. Okay. In this scenario, it's equal. So we can say function Fn is O of log v to n. So let's use some real. So this is how you prove that. Okay. So all you have to do is remember this thing. And let's go and use some numerical values so you guys have a better idea. So let's say Fn is log 2 to the power n, not 2 to the power 2, to base 2n. So we can say log 2n equals, let's use base 10. Sorry, it should be 2. So we all know log to base 10 is a constant. Its value is 0.3. If I'm not mistaken, this is the value. Okay, so it's a constant. So we can say log 2 to n, this should be 2, there we go, is equal to constant times log base 10 n. Because of that, we can say Fn is so yeah, that's how we do it. All right. So that's the last of characteristics of big O notation. And hopefully you guys have an idea what big O notation is. It's just the upper boundary. That's all. Don't think too much about it. It's just the upper boundary. All right. So now let's talk about big omega notation. So what is big omega notation? Big omega notation gives us the lower boundary. So big O gave us the upper boundary. Big omega gives the lower boundary. So over here we have a definition. It's the same thing. The only change is the symbol changed. So now Fn is big omega of Gn if there exist positive numbers C and N naught such that Fn is greater than or equal to C times Gn for all N greater than or equal to N naught. So that's a heavy definition, but it basically means the same thing. It means that after a particular N naught value, Fn has to be greater than C times Gn as it reaches infinity. So after the N naught value, Fn should always be greater than C times Gn for big omega. In big O, C times Gn had to be greater than Fn for all values after N naught. So there can't be a situation where after a particular point, C times Gn goes above Fn. So after N naught, Fn has to be greater than C times Gn for Gn to be big omega of Fn. So I'm talking about big omega notation here. I finished talking about big O. All right. So let's try a quick example. So over here we have Fn. So 5 times n square plus 8n plus 7. And then Gn, I take n squared. So how you take n squared as the candidate of Gn? What you do is that in the Fn, you identify the most dominant term. Most dominant term is the term with the highest uh, what you call it. So over here it's n squared. I forgot the word what you call this. So this is the most dominant term. So why we ignore other values is because as we go to the infinity, the contribution done by these values to the overall value of Fn becomes less significant. So let's say we go uh, to a value where n is equal to 1 million. So Fn should be 5 times. So if we say, so let's quickly say, okay. So let's say n is 10 to the power of 6, 1 million. So Fn is going to be 5 times. Okay, how to erase that? That's 5. 5 times 10 to the power of 6 square plus 8 times 10 to the power of 6 plus 7. So as you guys can see, Fn is going to be vastly influenced by this dominant term. So it's 10 to the power of 12 times 5. Then you have 8 times 6 and then 7. So the value of 7 is almost, you can ignore that completely because it doesn't contribute at all. So because of that, as n becomes a really large value, the less dominant terms become, their contribution becomes less significant. Therefore, we only take the most dominant term, and we also remove the coefficient of the most dominant term. So in this scenario, it's 5. So we remove 5 because we are only interested in finding the class a particular function belongs to. So whether this function belongs to the n squared class or n class or n cubic class or like that, to finding out to which class it belongs to. All right. So I got the candidate for Gn. Now what I do is that I apply it to the equation and see whether it satisfies. So if I use C, if I use 1 for the value of C, so obviously Fn is going to be greater than Gn. Therefore, we can say Fn is big omega of n squared. All right. So that's big omega. Okay. Hope you guys have an idea. Uh, let's today I will cover only the theories, and in another copy I will do all the practicals and go through some questions and stuff. When I do that, you guys will have an idea. But when I do that, make sure that you guys have finished watching this. So then I won't have to go through theories again. So we can base only focus on questions. All right. So we have the so yeah. So that's big omega notation. Big omega notation gives us the lower boundary of a function. Then we have big theta notation. All right. So this is the definition of big theta notation. It's very similar. The only difference is now instead of one inequality, there are two. So for both inequalities, function it's the same function is used, Gn. So the condition is that what if what if you multiply Gn by a particular C2 value, it should be greater than Fn after n naught. And if you multiply the same Gn by another C1 constant, it should be less than Fn for the same n naught value. All right. So let's look at this graph quickly. So over here we have Fn, this thing. And over here we have C1 times Gn. And as you can see, after n naught, C1 times Gn is less than Fn, where C2 times Gn is greater than Fn. So one thing you guys can see over here is that the n naught isn't shared between these two functions, these two comparisons, these two boundaries. All right. So for the C2 times Gn, it goes above Fn from the beginning. For C1 times Gn, n naught is over here. So let's say that there are two functions. Okay. Hopefully there's enough space here. Can I minimize the size? Only the color. It's fine. Okay. So let's say we have this Cartesian plane. So over here we have this. So this is Fn. Okay. And there's this function. So this one, let's call it C2 Gn. And there's another function that goes like this. Let's call this one C1 Gn. Okay, that's Gn. Okay, and if you observe the points where these two functions cross, okay, so let's call them, let's call this one N2 and N1. Okay, because N1 crosses the F1 from here and N2 crosses uh, N2, sorry, yeah, this above boundary uh, crosses F1 from here. So the value we take for n naught is the greater value of these two. So because n1 is greater than n2, we say n naught is greater to n1. So that's what has happened over here. If I change the colors quickly, uh, sorry, this. Okay, over here, uh, oh, over here, this is n1, and sorry, that's n. No, it's n1, and n2 also over here. Okay, let's say it's n2. N2 is over here. Because N1 is greater than N2, we took N1 as N naught. Right? So yeah, that's how you find out the N naught. So that's big theta. So what big theta has to be is that there should be a Gn function. Once you multiply it by Cn, C2, it should be above Fn after a particular N naught value. And once you multiply that same Gn function by C1 value, it should be less than Fn. If so, we say Gn is, so Fn, if so, we say Fn is big theta of Gn. So same thing over here. There's another way to find that out. It's that if a function Fn is big O and big theta of the same function Gn, we can say Fn is big theta of that same function Gn. So if you have a function uh, that belongs to, let's say, big O of n, and it also belongs to big omega of n, then it also belongs to big theta of n as well. Okay. So here we have an example. So we have 5n squared plus 8n plus 7. So we get the Gn value in the previous method I told you guys. You ignore all the non-dominant terms and remove the coefficient from the dominant term. Coefficient is 5. Okay, we remove that. And then I include those values to this inequality to see whether it's satisfied. And it is satisfied. So because it is satisfied, I can say Fn is big theta of n squared. So one trick to find out values of C2 and C1 is that always apply 1 to C1. Alright. And to C2, what you can do is, I think it's better if I use white. Okay, so what I can do is that over here, the function is, no, it's not the one I wanted. Okay, so here, function is fn squared plus 8n plus 7. So you use these coefficients and write it like this. Then you get what? 20 squared. So, and you can use this value as C2, and it will be equal. Okay, over here it should be equal, actually not greater than. This symbol should be equal. So if you use any value that's greater than 20, then it should be greater than. For now, it should be equal. That's a small mistake. Somehow, yeah. So somehow this the definition is satisfied. So we can say Fn is big theta of n squared. All right. So what do these functions tell us? Big O gives us the upper boundary, which means Fn will never grow faster than Gn. Big omega gives us the lower boundary, which means Fn will never go lower than the lower boundary, which is Gn, which will never grow slower than Gn. And big theta tells us Fn will grow in the same rate as Gn. So it's about the rate. Okay, it's not about the value, it's about the rate of change. So big O tells that the highest rate the function will change is Gn. It will never grow faster than that. Big omega tells us the function will never grow slower than the Gn. Big theta tells us that the function will always grow in the same rate of Gn. Alright. So these notations are used to analyze functions. How do we use them to analyze algorithms? Is that you convert an algorithm into a function and apply these notations into that function in order to analyze the algorithm. You can't analyze an algorithm using these notations, you analyze the function. So there are common misconceptions and myths about these three notations. That is that big omega gives the worst case of an algorithm. That's not true. Big omega gives the upper boundary of a function. It doesn't give us the worst case. It can be used to describe the worst case, but big omega doesn't give the worst case. It gives us the upper boundary of a function. Same way, big omega doesn't give us the best case of an algorithm. It gives us the lower boundary of a function, and that can be used to describe the best case of an algorithm. Same thing with theta. It tells us it gives us the what? It doesn't give us the average case. It gives us a tight boundary which tells that the function grows in the same rate. All right. So that's about it for these three notations. It's a very small copy. Okay, I will do this in 3 parts. So that's part 1. Over here, I went through all the definitions and stuff. In the next copy, I will tell you guys how to apply limits to find to evaluate the proper notation for a particular function. All right. So that's it for this copy. It's a quite small one. Hopefully, you guys have a idea what big O notation and what other two notations are. If you don't have, or if you feel a little bit confused, then drop me a message and I'll clarify everything. Or if you guys have any recommendations or anything, just drop me a message, or anyone in Ravindu, Hesandar, Isum. You can drop and give recommendations or complaints or anything to any 4 of us. If you can't complain to my face, it's okay to go and tell it to the other guys. Okay, so give us feedback and we will change our approach based on your feedback. Okay, so that's it for this one, and hopefully everything clears out, and see you guys in the next copy. So yeah, goodbye, and hope you guys have a great day.